Okay, let's keep going in section 3.3. We're trying to find zeros of a polynomial. And example 2 says just factor f of x into linear factors given that k is a zero. And so let's think about just what that means. If negative 3 is a zero, then the factor theorem tells us that x plus 3 is a factor. It also tells us that f of negative 3 is equal to 0, which means the remainder from the synthetic division is going to be 0. So we can start factoring, right? We know what the first factor is. It's x plus 3, but what's left over after that? Well, we'll see what that is by doing the synthetic division. So let's do some synthetic division. Let's take a negative 3 out in front, and then let's put 6, 19, 2, and negative 3 inside. And then let's go through the calculations. The multiplication and then an addition makes 1. Multiplication and then addition makes negative 1. Multiplication makes 3. And then addition makes 0, which is exactly what we had to have, right? We knew that the remainder was going to be 0. So that's a good way to check that our work is going okay. Okay, and then the division algorithm tells us how to write out f of x. So f of x is equal to x minus k would be x minus negative 3 or x plus 3 times q of x. The quotient starts with a coefficient 6 and an exponent of 2, because f of x starts with the third power, then the quotient will start with the second power. So we'll have 6x squared plus 1x to the first minus 1. And you see we have factors, and you can verify that x plus 3 times 6x squared plus x minus 1 really does multiply out to f of x that we were given in the problem. We're not done yet. The problem says we need to find linear factors, and so linear means that the degree of the factor is 1. Here's x to the first here for x plus 3, but this is a quadratic factor. And so this quadratic needs to be factored into two linear factors. And so we can do that with factor by grouping, or we can factor mentally. Let's see, I think we're going to wind up with a 3x and a 2x and a 1 and a 1. And then if we put a plus sign here and a minus sign here, then that should do it. Take your time to verify that those factors are correct. And that's all we're asked for in this problem. Find the linear factors. So that's the answer. It might be nice to go one step further and find the zeros. So to do that, remember, to find the zeros is to set f of x equal to 0. And f of x is just x plus 3 times 3x minus 1 times 2x plus 1. And then we just set each factor equal to 0. So x plus 3 equals 0 gives us x equals negative 3. Let's go ahead and box that one up. I think I can fit all this in the corner of the page. Let's do 3x minus 1 equals 0. If you add 1 and divide by 3, you get 1/3. And we can box that one up. And then there should be room right down below to write the last one, 2x plus 1 equals 0. If you subtract 1 and divide by 2, then you have x equals negative 1/2. And so remember, our factor theorem says from each factor there's a 0. X plus 3 gives us negative 3. 3x minus 1 gives us 1/3. 2x plus 1 gives us negative 1/2. Let's go on and do another example. For the following polynomial, 1 0 is given. Find all the other zeros. So that's essentially what we just did in the last problem. So we can do it again. You might even want to try pausing the video and try to do the problem on your own first. Three is a 0 means f of 3 is equal to 0, and it also means that x minus 3 is a factor. Oh, and I guess one more. When we do the synthetic division, the remainder will be 0. So what we're going to do is we're going to solve h of x equals 0. And we can write that as x cubed minus 7x squared plus 17x minus 15 is equal to 0. And the way we solve this is by factoring. And the way we factor this cubic polynomial is to use synthetic division. So let's do the synthetic division over here on the side. Let's put the value of k out in front. And then 1, negative 7, 17, and negative 15. And then we can bring down the 1. And then multiply and add. Multiply and add. Multiply and add. And again, the remainder comes out to 0, just as it has to, according to the problem. So then, let's see here. I said it a few minutes ago in the first example, in the last example. Let me go ahead and write it out right here. The division algorithm tells us that we can write f of x as x minus k times the quotient q of x plus r. And so that's what we're doing here when we factor, when we write the answer from the synthetic division, when we factor this polynomial. So we start out with x minus k. K is 3. So we have x minus 3 times the quotient. And the quotient is here with coefficients 1, negative 4, and 5. And since the polynomial was degree 3, the quotient is degree 2. So we're going to have 1 times x squared minus 4 times x plus 5. And then there's a plus r at the end, but the remainder is 0. So we don't need to write anything there. And so we have our factors. Now, can we go ahead and factor this quadratic? Try for yourself. I don't think it's going to work. So we'll just leave the quadratic as it is. We'll go ahead and set the linear factor equal to 0 and get x equals 3. And of course, that's the 0 that we already knew, right? That's the 0 that we were given originally. And so then the other two factors are going to come from solving the quadratic. X squared minus 4x plus 5 equals 0. Of course, when we have a quadratic, we don't have to solve by factoring. Factoring is nice, but it doesn't always work. So we fall back on the quadratic formula. We write x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And so we have x equals 4 plus or minus 16 minus 20 is negative 4. So we have the square root of negative 4 over 2. 4 plus or minus the square root of negative 4 we learned to write as 2i. So these zeros are not real numbers. We can do one more step. We can distribute the 2 in the denominator to each term in the numerator. 4 over 2 is 2, plus or minus 2i over 2 is just I. And so we could just go ahead and box that up. Or maybe it would be nice to write out all three zeros together. The first 0 was 3, the next 0 is 2 plus I, and the last 0 is 2 minus I. And so we can write our solutions in set notation, and we're done.